Okay, YouTube, in this video we're going to continue exploring how to solve exponential equations, but in this video we're going to focus on using logarithms to do so. So in our last video, we looked at what we call the one-to-one property that says, well, if at least you had an exponential equation and both sides of the equation had similar bases, then what we could do is we could equate their exponents. And so this is really convenient for things like, hey, 2 to the x equals 32, where we can write 2 to the x is equal to the 2 to the fifth. Since they both have a base of 2, then x is 5. That works when you have a one-to-one situation, or that you can write both sides having the same basis, but there are plenty of situations in which we can't do that. So what we're going to do to solve an exponential equation is use their inverse, and we're going to use what we call a logarithm, of course. So we say in order to solve usually using logarithms in order to solve exponential equations, what we're going to do first is we're going to isolate the exponential expression. So for instance, when you look down here on checkpoint 2, this says 5 to the x equals 134. I would say that this exponential expression is already isolated on the left. That is to say, I don't have anything out front like 2 times 5 or 5x and then a plus 1 over here on the right that I'd have to subtract first. So isolate the expression, and then what we're going to do is take the common logarithm on both sides of the equation for base 10, take the natural logarithm on both sides of the equation for bases other than 10, and then it says simplify using one of the following properties. So in terms of properties here, we have this. ln of b to the x. Remember that our power property says that when you take the natural log or any log of something to the power of another thing, we can pull that power out in front. Likewise, if we were to take the ln of e to the x, because the ln is really the log base e of e to the x, because these are inverses, these two expressions cancel out and we get left with just the x. Or likewise, since this is log base 10, a common log of 10 to the power of x, those cancel out and we get left with x. I would say in general, log base b of b to the x is equal to x. So in other words, we have exponential expressions that can be undone with logarithms, but we just have to use the same basis. So same basis. So let's take a look at what this would look like when it comes to solving equations. Starting with letter A here, it says 5 to the x equals 134. The idea here is if I want to undo an exponential thing, I'll get it by itself on the left side, and then what we'll do is we'll take the log of both sides. It just so happens that I'm going to choose to take the log base 5 of 5 to the x, but only because I know that the log base 5 and the 5 cancel out and give me just the x. So I'd say I have to do the same thing to the right that I did to the left, so log base 5 of 134. So essentially what we get here is this. Well, then x is equal to log base 5 of 134. And so in order to evaluate this and get a decimal, what we're going to actually have to do is use our change of base formula. It says we could also evaluate this by doing ln of 134 over ln of 5, or we could do a common log if you want to do a common log. So we'll take a look at this. We say 134. We'll take the ln of that, and then we'll divide by 5, the ln of that, and we get about 3.043, so approximately 3.043. And this is certainly something that we can go plug back in and check. If I were to take 5 to the power of, let's do this, we say 5 to the power of, I think I can do it thusly, and we have 3.043, enter. You see that we get approximately 134. We didn't get exactly because I under-rounded this. So, but in terms of solving an equation, we could just go ahead and take the log of both sides here. So looking at letter B, it looks like we have 10 to the x equals 8,000. What we'll do here to solve this is isolate this expression, which it already is, and we'll take log base 10 of both sides, since we have a base of 10 on our exponential expression. So we have log base 10 of 8,000. That's a base 10 then. So we get this here. We get x equals log of 8,000. I'm not going to write base 10 this time because it is absolutely a common log. And if I were to type in 8,000, there's my log base 10 button. We have about 3.903. So x is approximately 3.903. So you can see how logs come in handy to undo exponential expressions by canceling them out. So let's take a look at a couple more exotic situations with solving exponential equations. So with checkpoint 3 here, it says let's go ahead and solve this. 7 times e to the 2x power, that minus 5 equals 58. So let's find the solution set and then use a calculator to obtain a decimal approximation to 2 decimal places for the solution. So here's what we're going to need to do first. In this particular instance, we need to isolate this exponential thing, which is this e to the 2x power. So with my 7e to the 2x minus 5 equals 58, we're going to start by adding our 5 to both sides. So when we add 5 to the right side here, we get a 63. So we have 7e to the 2x is equal to 63, and then we'll divide by our 7. We need to get the 7 out of the way. But once we do this, you can see how we end up with, let me just put it up here, e to the 2x, and this is equal to 63 divided by 7, which is 9. So in order to get rid of this, we need to take the log, but with the base of e on both sides. So what this means in our particular instance, we're going to take the ln of both sides here. And in terms of what we can do with this, well, we could say that the ln of e, those are inverses and they cancel out. So we get left with 2x equals the ln of 9. And then if we split this in half, we would get x equaling half of the natural log of 9. So as far as the exact value, this is what we'll refer to as the exact value. And certainly we want to get a decimal value here, as the instructions manage to tell us. So we'd say, okay, 9. We want to take the natural log of 9 and then divide this by 2. So we get approximately 1.09, where we round that up, so 1.10. So x is approximately 1.10. And I would encourage you to check this back in the original equation. So now, for checkpoint number 4, what I want everybody to see here is that we have two exponential expressions. So I'm going to be the first to tell you that this particular instance is going to involve some heavy algebra. But when you have two exponential expressions and they do not have the same bases, this is not one-to-one. So I can't just go ahead and set the exponents equal to each other. So in terms of what property we're going to use here, I'm going to start by saying we'll just take the ln of both sides, just right off the bat. Since they're both exponential, what's going to happen is when we take the ln of this, we can do some rearranging. So what I know about properties of logarithms, oops, let me fix this, is that these exponents here, if I'm taking the log of something to the exponent of another thing, what we can do is we can pull them out in front. So what we're going to end up with here is this. We get 2x minus 1 times the ln of just the 3 part. On the right side, we get x plus 1 pulled out in front times the ln of 7. So here's where the algebra comes in. We're going to distribute our natural logs through each of these quantities. So we get this 2x natural log of 3 minus the natural log of 3. On the right side, we get x times the natural log of 7 plus the natural log of 7. And now our job is to isolate the x. So just like with any other equation, just know that ln of 3 and ln of 7, those are just numbers. So what I'm going to do is I'm going to subtract, say, this x ln of 7 from both sides minus x ln of 7. Okay, and what we end up with is this, 2x ln of 3 minus x ln of 7 minus the ln of 3. And on the right side, this would be gone now. We just had the ln of 7. So one thing I'm also interested in doing is getting this ln of 3 over to the right side. So we get 2x ln 3 minus x ln 7. And then on the right side, we just have positive ln of 3 plus a positive ln of 7. So here's where the trick comes in, where we're going to get our x out of this. We're going to factor the greatest common factor out of both of these terms. And what they have in common is that x. So what's left is really just 2 ln of 3 minus the ln of 7. All of that times our x. And what that's equal to is this ln of 3 plus the ln of 7. So it seems really uncomfortable, but what we're going to do is we're going to take everything on the right here, and we're going to divide by this 2 ln 3 minus ln of 7. So our final solution, I'm going to try to write this small over here. We say x is equal to this ln 3 plus ln of 7. We said ln 3 plus ln of 7. But all over this quantity here, 2 ln 3 minus ln of 7. Okay? And so we do want to get two decimal places on this one. As a matter of fact, what I'm going to do is I'm going to get out my graphing calculator for this particular instance. So typing all of this in, I would say that let's type in everything on the top first, starting with the ln of 3, which we need to put an end parenthesis on. So we get ln 3 plus ln of 7. So all of that is our numerator. We're going to divide by, in parentheses now, 2 ln of 3, end parenthesis, minus ln of 7. And then another end parenthesis to surround everything in the denominator. But what we get here is about 12.11. So we say x is approximately 12.11 in this particular equation. But I would say that study this particular instance. You see it pop up every once in a while. But for the most part, we can just use logs to undo exponential things. Cheers.